Hello, this is our fourth and final guest episode on the Standard Model with Professor Ananthanarayan of the Indian Institute of Science, Bangalore. If you haven't watched the previous episodes, you should watch those before you watch this one. Professor Ananthanarayan is professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore, where he has also served as head of the department and guided several PhD students, including at least one of my own former colleagues. He did his BTech at the Indian Institute of Technology, Madras. Switching to physics, he then earned a master's in science and a PhD in physics from the University of Delaware in the US. Anant is a member of the editorial board of the European Physical Journal A and the Indian Journal of Pure and Applied Physics. His research interests are in the field of elementary particle physics and quantum field theory. He works both at the frontiers of the standard model and high precision, and also at finding signatures of interactions that lie beyond the standard model, that is, at finding new physics that can be uncovered at the International Linear Collider. He has also worked on dispersion relations, on the chiral symmetry of the strong interactions, and on grand unified theories and supersymmetric models. Anant is a prolific writer, a popular speaker, and a recipient of the Homi Bhabha Fellowship and the Rustam Choksi Award for Excellence in Science. With that, it gives me great pleasure to invite Professor Ananthanarayan to join us.
I had promised you earlier that I will tell you a little bit about gauge theories, because everything that I talked about is gauge theories to give some kind of substance to this idea and not just words. I should show at least display a few equations. So should I do that?
Yeah, go ahead, please.
Yeah. So we already said what is a gauge theory, and we have already convinced ourselves that electromagnetism is a prototype of a gauge theory. Okay? And so let us take electromagnetism, which any BSc student or even 12th standard student has somehow seen. And it, of course, involves two fields, the electric and magnetic fields. And we know that two of the laws which pertain to static fields say that the divergence of the electric field is 4 pi times the charge density. And the fact that we do not observe any, why did this thing turn blue? Yeah, oops. Okay. Why did it turn blue? Okay. And we know that there are no monopoles in the universe, which would say then that the divergence of V is equal to 0. Why are there no monopoles in the world? We actually don't know. It's just experimental finding. And we have Earth-based experiments which have tried to see if there are cosmological monopoles that pass through it. And there are stringent bounds in these.
One of my professors at Stony Brook, Alfred Goldhaber, spent his life trying to pursue
yes.
monopoles.
Yes, yeah. So, but we also know that there are primordial magnetic fields and there are magnetic fields in the galaxy and so on. And so if there were monopoles going past them, then they would, of course, attenuate the strength of these magnetic fields in the galaxies and so on. So there is a famous bound known as the Parker bound, which gives a bound on the possible number density of monopoles. In some Earth-based experiments, there's one called macro, which today has a bound in certain velocity regimes for monopoles, which actually is better than the Parker bound, but that's only one specialized result. Then there are two Maxwell's laws, which has to do with electrodynamics. First one talks about the curl of the electric field, which is then related to this changing magnetic fields, and this is basically Faraday's law written in this way. And then you also have Ampere's law written this way, where the changing current over here gives rise to a magnetic field. But it's possible to reorganize these Maxwell's laws in terms of an object that we call a field strength tensor, and you've already seen it in one of my earlier slides. So let us just group it in this particular way and write it as a 4 tensor, 2 by 2 tensor, with both space as well as time indices, because these Maxwell's laws, as you see, already unify space and time. I mean, the curl here has the time derivative of the B field, whereas here the curl of B has the time derivative of the E field. So we necessarily have to be able to talk about the space and time components on a unified framework, except that here the E and B fields carry this three vector arrow on top of their heads. So each of these has three components, Ex, Ey, Ez, and it can be organized in this particular way. Um, in a world where there were magnetic monopoles, then this del dot B would change. There would be a 4 pi times rho of the magnetic field, and the first of these curl equations would also change. And there would be a corresponding monopole current on the right hand side of this equation over here. In which case, you would have a version of this F mu nu, call it F mu nu tilde, where the E and B fields actually the roles are reversed. And that is called duality. But in nature, we don't observe this duality. So this is the set of Maxwell's laws that we have, which is also phenomenological. This is how nature seems to be. And you can also collect the density as well as the current and organize it in a 4-vector Lorentz 4-vector in this way. And then write down at least two of the Maxwell's laws in this particular way as a partial derivative of this F mu nu equal to 4 pi times divided by C times J nu.
And where
However, there's a further,
and where
yes.
del mu has the components minus 1 upon C del del T and del X
Yes,
del Y
yes,
del Z.
yes,
Yeah.
yes. Yeah, thank you. However, the structure of the Maxwell's laws already suggests that you can do something more to find a even better way of representing these. The fact that the divergence of B is 0 says that there has to be some other field denoted by A, 3-vector A, so that B is the curl of this A, so that immediately del dot B is equal to 0, because the divergence of a curl is 0. It has to be. But then this is not enough, but then we throw in, because we are now interested in 4 vectors. Okay, so you want a 4-vector. So this provides only 3 components. So let's take an A naught and put that equal to the electrostatic field V over here, and organize V and A together to call it an A mu. Right. So if you did that, then the E field is obtained in terms of this V and in this vector A as minus del V minus 1 by C dA by dt. Now, isn't that nice? But that said, it turns out that this A mu is not unique, but if you just add to it always this kind of a gradient of some other field lambda, any arbitrary field lambda, then the field equations are left invariant. The B and E are the same whether you use A mu or A mu prime. This is already a gauge transformation, and is a property that we had already introduced at the time we had studied the Dirac field. Okay, so this is a very nice thing. So once again, to recall, so the way why these slides are repeating these things is, I first wrote the main part of this, like the UPSC exam, and then I decided that I need a preliminary part like the JE, and that's how I did the preliminary slides, and that's why there's a little bit of repetition between the two. So how does this work in a theory with electrons? And we have already seen that this is what the Dirac equation looks like. This is the Dirac equation without interactions. And then we said that we want invariance of this local or global symmetry is already present. So we turn it into a local one by promoting this theta field over here, theta parameter sitting over here. That lives in the invariance relation of this L as a function of X. And if you do that from the chain rule of differential calculus, you will see that This is invariant if you introduce another field known as A mu and demand that this A mu has the same gauge transformation law. Now, my kind host Sukumar is so smart. I mean, he just picked up the fact that I had missed a factor of C over here. Okay. It's totally mind-boggling how he did that. Sorry about that. There has to be a missing
No,
C over here.
that's just my editorial experience,
No.
proofreading experience. Yeah. Go ahead.
But then, since we have this Lagrangian, let me also try to educate the students as to why this thing should be correct. Okay. So this Lagrangian, as we already said, is like an energy, but what we are calling the Lagrangian is really a Lagrangian density. Okay, it's a density. So mc squared, has to be an energy. E equals mc squared. So this has the dimensions of energy, but I said that this has to be a Lagrangian density. So that means that this particular combination psi bar psi has dimensions of inverse length cubed. Okay, there's dimensions of inverse length cubed. But if you look at the first term over here, the same psi bar psi is here, and therefore, and it has an additional inverse length over here. So that means this h bar c should be such that it cancels this inverse length to the fore. So that means that h bar c had better have dimensions of energy times length. And it's very important that there is a combination of h bar and c, which is often set equal to unity in the system of natural units, but it has a numerical value of 197 MeV femtometer. It's a very useful combination of numbers. H bar C is 197 MeV femtometer. I know there's a lot of information overload over here, but what to do? That is the nature of this game. So you see, so if you have this, a very physical way of understanding what a gauge theory is, you can start out with Maxwell's laws, then you can introduce the A field, then you see what is the gauge transformation. And then if you start out with the Dirac-Lagrangian, for instance, you could also start out with Lagrangian for scalar fields and do a similar exercise. Then you will find that the same symmetry, the same mu going to d mu lambda, will have to be what it is in order for this Lagrangian to remain invariant. So this is like gauge theory is made simple. But this is a very simple thing where the gauge symmetry is just a multiplication by a phase factor like this. What about more complicated gauge theories? How do you construct them? So we have to do it again by analogy and try to build it up, except that the Dirac field here would be replaced by a more complicated set of fields, and then you have a more complicated set of transformations among those fields. Okay? But the idea is the same. And that's what was done by Young and Mills. So, but before we do that, if you just take this as it stands over here, this doesn't yet reproduce for you Maxwell's laws. Why is that? Because it just has introduced for you. So if you collect this psi bar gamma mu psi and call it J mu, then there's an interaction between the electron current and the photon field over here, mu. But what about dynamics for the photon field itself? Okay, what about dynamics? In order to have dynamics, you need to have derivatives. You need to have kinetic energy for the electromagnetic field. And that is done by using this object that we had in the slide, which is the F mu nu that we introduced over here, so the F mu nu that we introduced over here is in terms of E fields and V fields. But we would like to replace this by various derivatives of the A field. Okay, this is in terms of E and B. We said that there is a very nice and friendly A field, not just one A field, but a family of A fields that are related by the gauge transformation. So how do we express this object F mu nu in terms of this A field? But we already know explicitly what is the relationship between the E field and the A field. And you can write a dictionary to translate from one to the other. You can ask ChatGPT to do it, or even Google Translate or whoever. It turns out that the right way of introducing this is with minus 1/4 F mu nu, where F mu nu can be expressed in terms of A, which I have forgotten right over here, and I leave it as a homework exercise. It's actually the anti-symmetric combination of d mu a nu minus d nu a mu. Okay, so you can just write it that way as f mu nu in terms of d mu. It's an antisymmetric field tensor. So it turns out that, as I already said, what about if you want to have more complicated gauge interactions? So we could do this by introducing, let's say, two species of Dirac fields, call them psi1 and psi2, and you want to rotate them amongst each other. You can rotate them using two U1s, but that will be totally boring, stupid thing to do. But something more interesting, like having unitary transformations among them. So in order to do that, then you will need so-called generators of such an SU2, which, believe it or not, are the same Pauli matrices that you have encountered, because this SU2 is related to spin, and it's also rotation, so on. So same thing that shows up. So if you want to rotate it amongst each other, then the SU2 has three independent parameters. Earlier we had only one parameter, theta of x. Now you'll have three independent parameters, theta 2, theta 3. Not only that, associated with this theta, you needed an a mu. Now you will need three a mu1, a mu2, a mu3. But there's a very interesting thing, that these are not just three copies of the same a mu. These are intimately interlinked by each other through these SU2 operations. And what will happen is that the field strength tensor, now what I had called d mu a nu minus d mu a mu, which is antisymmetric, can bring in another term which involves, for f mu nu for the first field, one over here, can involve the commutator of a mu2 and a mu3. Commutator means a commutator of a b is ab minus ba. So the antisymmetry here can be extended when you have a family of gauge fields. That is how this Young-Mills theory is constructed in this way, and it has a non-trivial property which was not present in electrodynamics.
So that brings in the non-abelian aspects of that.
Yes, yes. So whenever there is commutativity in these group operations, they are in honor of Abel. They are named as abelian groups. And if they are non-commutative, which is already known to Abel, it's called non-abelian gauge theories. And physically, in non-abelian gauge theories, the field strength tensor will have bilinears of this kind, so that when you put it back into this f mu nu, these bilinears can produce new kinds of interactions, which represent the fact that you can have vertices in the theory among the gauge particles, which is not seen in electrodynamics. In electrodynamics, I had introduced Delbruck scattering, if you remember, so light on light scattering, but there was no direct vertex of two photons giving a third photon. There's no such thing. So you need these non-abelian theories when you want to have gauge bosons to interact with each other. But these are not arbitrary interactions. The gauge invariance fixes the strength of these interactions. So the theory is very tightly bound, very tightly constrained. These are not arbitrary things. So at first sight, it seems like we are doing all kinds of things, like assembling various bits and pieces, but not really. It doesn't work like that. And yet, at the stage, there are no masses for these force carriers, either in electrodynamics, which is fine because then we know that the photon has got an infinite range and is massless. But then what do you do about the weak interactions? Because we know that the force carriers are massive, because the weak interaction is very short ranged. So that can be dynamically generated by scalar fields through the Higgs mechanism that we already discussed some time ago. Okay. And this answers Sukumar's first question from this morning, which is about how parity violation, this SU2 cross U1 electroweak model, does not allow explicit masses. So no explicit masses are allowed for force carriers. It has to be generated by the Higgs mechanism. But the same set of Higgs fields that do the Higgs mechanism also will allow you to introduce masses for fermions through the Yukawa couplings, which I think we had already discussed earlier today. All this, of course, would be very empty without some numerical examples. Okay, it is not just talk. So let us see. There are some numbers that we can. So all the above said, let us see what it really means. To talk about interactions. And it's not just about vertices, but we also have to do the full perturbation expansion and all these things. So this, I think we already mentioned in the preliminaries, and we had already seen these diagrams already, how starting from the basic vertices, you have to construct the higher order perturbation series. It's the same vertices. It's not like you can invent new vertices. The vertex is already fixed by the Lagrangian itself, by the interaction term. So you have various diagrams that you have to draw with the same vertices. At one loop level that I have over here, they are quite straightforward. But as the number of loops increases, then it becomes quite a complicated problem in graph theory, as well as in, you can have non-planar diagrams, all kinds of topologies of these diagrams. But the basic rules are somehow known, and their implementation, which today is done for standard model on the computer, generating millions of diagrams if the need arises, as is the case, let us say, for QED, 4 loops or 5 loop order. All these things are done. Not only that, the basic notion of regularization and renormalization, which can be illustrated at the 1 loop level, also carry through to all higher loops. They're technically very challenging, but in a sense, all these things are known. So as I said earlier, and we have seen this again and again, knowing what the rules are, we can compute, for instance, matrix elements for... it's not just about drawing diagrams, but there's a meaning to every one of these, that the momentum of the incoming particles are known, the momenta of the outgoing particles are known, and you know what kind of reference frame you have to do this calculation in. Could be the
basically
mass. Yeah.
So basically each diagram corresponds to an amplitude or an integral, right? Which can be evaluated
at a fixed order, at a certain order in the perturbation series.
Yeah.
And so that you will have a concrete answer for, let us say, the Bhabha cross section at a particular order will be a known function of the masses of the particles, of the momenta of the central mass energies, and as well as the angle of at which your detector is placed. So it will be some known answer. We all know what it looks like for Rutherford scattering, right? There's a 1 by sine to the power of 4, theta by 2. We know that expression. So there'll be an analogous expression for the differential cross section for any process at a fixed order in perturbation theory. So that is what is physics. Cross-section, lifetime, cross-section, lifetime. These are ultimately only observables that we have, or you can have a branching ratio or a width or a particular, number of events in a particular channel. So that is what is known as physics, is what your laboratory apparatus can see in terms of the theory. A simpler diagram than Bhabha scattering, for instance, is E plus E minus to mu plus mu minus. It's a very simple diagram like this. So which in QED, finally the total cross section is a very beautiful answer that looks like this: 4 pi alpha squared by 3s, where I have put h bar equals c equals 1. So let's try to understand this. This 4 pi here comes from the solid angle of the integration, and it must have dimensions of a cross section finally. So energy squared, you'll already recall MeV femtometer squared is the value of h bar c. So if you put back suitable powers of h bar c, you will get this in terms of femtometers squared, which is the dimension of cross.
Remind me again, what is S?
S here is the sum of the beam energies of E plus and E minus in the central mass. That is square root of S. So S is the square of the central mass energy. Square of the central mass energy.
Thanks.
So very beautiful. Yeah. So let us compare this with some well-known cross-section. For instance, you have the Thomson cross-section. which is a classical electromagnetic result, which looks like this. It's 8 pi by 3. There's always in cross sections you'll get this factors of 8 pi. Here I have written it with the full glory of h bar c and so on, alpha divided by me squared. This is a very beautiful answer because the only energy at very low energies, only energy you can, at very low kinetic energies, is the mass of the electron, nothing else. That's why you see me c squared. This is the energy here, and then you have to square it in order to get a cross section. So if you plug this various values of the parameters of alpha and me, you will get a number of 0.665 barn. So this barn is a unit for cross section, which corresponds to 10 to the minus 28 meters squared. This can also be compared. There are other length scales in physics.
Barn.
Yeah.
Is that barn BARN or bar?
Barn, BARN. So
BARN,
that is just
okay.
some historical name.
Okay.
BARN. Bar is of course a unit of pressure,
right.
but this is a barn, BARN. So you often hear millibarn, you hear nanobarns, you get, and you talk about luminosity. So whenever you multiply a cross section with a luminosity, you're supposed to get a pure number. So luminosity is the number of the flux and so on in a particular experiment. So cross section multiplied by luminosity should give you a pure number. So luminosity is expressed in inverse femtobarn, inverse barn, inverse nanobarn, etc. So that barn times inverse barn gives you a pure number. So let's compare this, for instance, with the classical charge radius, and you could put that into this, and it is related to also the Thomson cross section. You can re-express this as in terms of the Bohr radius. You can find an expression for the classical charge radius. The other fundamental length associated with any particle is a Compton wavelength, which is given by h by MEC, for instance. You can also compute the Compton wavelength of W boson, which will then prove to you why the weak interactions operate at the subnuclear level. If you compute the Compton wavelength of the W, you will find that it is less than a femtometer. Okay? So that's how you know that it kicks in only at the subnuclear level and is the correct scale for radioactivity. I want to give you one more illustration of some cool stuff having to do with static properties in the Quark model. I already said that mesons are made up of QQ bar pairs, whereas baryons are made up of 3 quarks. 2 U's and a D gives you a proton. 2 D's and a U gives you a neutron. And then you can replace one of them by an S quark. Then you have a corresponding, mesons. So, for instance, possible to organize all the the lightest meson states on this plane where we have something known as the isospin, which was first introduced by Heisenberg in the context of trying to understand nuclei. So he said that as far as the strong interactions are concerned, if you turn off the Coulomb repulsion, the nuclei are basically invariant under the swaps of neutrons and protons. So this is seen, for instance, in mirror nuclei. So later this was extended also to pions to say that pi plus, pi minus, and pi 0 also have very nice transformation properties under this proposed isospin symmetry. So just like you have spin half, spin 1, spin 2, etc., you can have an isospin half, isospin 1, etc. So let us try to organize this with the third component of the isospin, which is denoted by this axis, I3. Okay, so let's try to put in the pions. So there's 3 of them. One of them had better sit at the origin. The other axis has the strangeness. The pions have no S quarks. So you can organize them on this plot and put a pi 0 in the middle and a pi plus in the pi minus. Now you replace one of the U or D quarks by an S quark. Then you get strange mesons. You get a K0 and you have a K0 bar. They sit opposite each other, and the K minus and the K plus. Okay, so this is very simple with just 2 quarks. And this is what is known as the pseudoscalar octet, which we already said was a 0 minus. There's one more member over here. How about trying to organize the baryons in this plane of I3 and strangeness? Okay, let's do that. So we already said that this is an isospin doublet. So let's put a proton and a neutron. There are no s quarks in this. Now let's replace one of the d and u quarks by one of the s quarks. You just put in one s quark, you get a bunch of states, which are all baryons, strange baryons. One of them is a sigma minus. Now it's an isospin triplet over here. It has one s quark. Yeah. So like so.
Just one
Yes.
one doubt. Here the pluses and minuses refer to the
These are the electric
isospin or to the
charges. You
charge.
can label them. You can label them with electric charge. That's a very nice thing about all this. These things also hang together in such a way that this is actually the electric charge.
But J3 is the
Newton.
angular momentum component. Is that right?
Yeah, the angular momentum of the state.
Okay.
So if you have two quarks, spin up, spin down, together they can either form spin 0 or a spin 1, just by angular momentum addition. Similarly, if you have three quarks, three spin half objects, then you can get a spin half or you can get a spin 3/2, right? So,
Yeah.
so half plus half times half times half. So that is a kind of calculation you have to do as far as the spins are concerned. And then you can get the spin 3 halves with all of them pointing up. So here, so you have the neutron and the proton as advertised, and then their strange components. They're called sigma minus, sigma naught, and sigma plus, and these are called the cascades of the capital psi, psi minus, psi naught, sigma naught, and then there's another one, so which forms a full octet. 1, 2, 3, 4, 5, 6, 7, and 8. This is called the lambda. It's called the baryon octet, and this the spin half with parity plus. Okay. The reason for introducing this is nobody asked so far, how do you know that there are three colors? What is the evidence that there are three colors? It's just all black magic. Actually, by studying this baryon spectrum, you'll be able to do that. Okay. For instance, let us now consider this Jp equals 3/2 plus so-called baryon decuplet. You have to cook this out of the three quarks. You have to put three quarks in, and you have three choices: U, D, and S quarks. Supposing there are no s quarks, then the following possibilities are there. All three are u quarks. Two of them are u quarks. One is a u quark. All three are d quarks. Why didn't we have such a thing here in the neutron and proton? Why is it that we didn't have, in the spin half sector, why did we not have something like this delta plus plus with three u quarks? Because it is forbidden by the Pauli exclusion principle, the way in which the spatial and spin quantum numbers are associated with these states. When you are in spin half, it is not possible to have full antisymmetry among the various quantum numbers. It's only possible when you have Jp equals 3 plus. And this is what proves that there has to be an additional quantum number which is hidden, which is what we identify with the hidden color that is sitting. So there are many indirect ways in which you can infer that there is an additional quantum number associated with the storm interactions. Not only that, it's not just about organizing, in the scatter plot and making things very nice. There are actually predictions, for instance, for the magnetic moment of the neutron and proton in such a Quark model. Yes. So this quantum number is not just some mathematical artifact, but it has to be sitting in order to understand this baryon spectrum. Not only that, there are other indirect sources from which we infer that there is a quantum number. For instance, this pi 0 decaying to gamma also involves the number of colors, which is consistent with 3. Then there's a ratio of the cross-section of E plus E minus to hadrons divided by cross-section of E plus E minus to mu pairs, which also supports the hypothesis that the number of colors is 3. I had already mentioned that the tau meson, the tau lepton decays into hadronic states. Even there, we can get a test that the number of colors is equal to 3. So, for a young student to start dealing with phenomenology and trying to understand where all this is coming from, they have to look at these different pieces. This is what I said. A standard model has many moving parts, and you have to fit it all in this. It's like a very sophisticated Mercedes or a BMW, which is highly engineered with, hundreds of chips that control the wiper, that controls the door, that controls the your boot, and it also controls the speed and the accelerator and everything. The standard model is a very complicated machine, but there are some things that you can understand. For instance, you can understand what is the steering wheel. You can understand what is where you keep your coffee mug. So things like this, simple things like this baryon spectrum and so on, are very evident, obvious things that any student can understand. So all this points to a consistent picture of relativistic quantum field theory based on the gauge principle, where we understand what the microscopic degrees of freedom. It doesn't mean that we know everything. We don't even know how to get a proton from quarks and gluons. We don't know how to get all kinds of branching fractions into definite states, but we keep trying. And everything that we do supports the hypothesis that definitely at low energies, the standard model is highly consistent. One recent piece of evidence to the contrary is this muon G minus 2, and there is still a lot of discussions going on in that. So one of the things that was really a prediction of the Higgs, which took a very long time to show because not enough energy was available in the accelerators that had been built up until the time of the LHC, and it kicked in and started to work, was the actual discovery of the Higgs, because its mass was not known. And it turned out that even at the predecessor to the LHC, which is the Large Electron-Positron Collider, the central mass energy was not enough to have produced the Higgs. So there was, in 2003 or so, there was a decision to shut down the LEP and to start the work for the LHC, and many people thought, oh, the Higgs is around the corner. Well, it was around the corner, but not quite, so the decision proved to be right to start the LHC in order to eventually discover the Higgs, which is today been found at the LHC, the Large Hadron Collider, where the two important multi-purpose experiments, the compact muon solenoid and the A-toroidal LHC apparatus, as it is called. So one last comment that I wanted to make was, even though we have these different manifestations of various sectors of the standard model, what if everything was born from some, mother theory? Just like we know that C2 cross U1 breaks spontaneously to give the weak interactions, and it gives the electromagnetic interaction. What if that there was some great unified theory which spontaneously broke and gave rise to the three different interactions that we have?
What is Q?
Yeah. Q is the energy. It's a scale at which a measurement is performed. So we had already talked about the renormalization group flow, that as you increase the energy of the probe, you will see the value of the charge changing, which is governed by the renormalization group equation, which tells you how a coupling constant in a theory runs as a function of the scale. So as you probe at higher and higher energies, perhaps from low energies, the coupling constants come together. The one loop beta functions actually are just straight lines. That's the reason why I have written it like this. For alpha inverse, it looks like this, where the slopes are given by the various beta functions. And for asymptotically free theories, they are negative, whereas the beta function is negative. So two of them increase. This is alpha inverse, we see. So this increases, and this is electromagnetism, which decreases. The alpha inverse decreases. So perhaps
these lines are what you mean by saying that
the values of alpha inverse
running coupling constants. That's the
exactly
values of the coupling constants change with the energy scale.
Exactly. And what if they all come together? And what is the nature of unification of the gauge groups of the standard model? It's not just unifying gauge groups, but all the representations of all the matter in the standard model also have to be unified. So this is a theoretical program that was started in the 70s, very beautiful in the sphere of ideas. And then if you unify the particles also, then you may have transitions between them because of the gauge bosons of such a higher symmetry. And it made predictions, for instance, for the proton decay, but so far there's no evidence that the proton decays. So these are all very beautiful ideas. It's all out of the box thinking. Maybe it's science of the 21st century, but that's where we are today. And the final question is, why is it that we have not talked about gravity? So just suffice it to say that we are over here at 100 GeV, whereas if you want to understand where quantum phenomena for relativity kick in, then you may have to consider the Planck length, or the Planck energy, which is a combination of the fundamental constants h bar c divided by the Newton's constant raised to 1/2 is 10 to the 19 GeV. So we are like 17 orders of magnitude away. So for all the standard model physics that we do today, there's no need to include gravitational effects. So this is what I had to say in slides.
So
but
you
let
might
me
need
also
you might need a collider the size of the galaxy.
exactly.
Okay.
Let me also share this for 1 second over here. So since Sukumar had asked me for references, this is the set of references that I had gathered. So one of the office staff asked me if I read all these books. The answer is obviously not. But I told her that this is like a lawyer's office, like lawyers have this or used to have these enormous volumes of the All India Reporter, because sometimes they need to refer to a particular case. So similarly, there are lots of books, and you may just say, hey, that particular formula that I'm looking for is actually sitting in this particular book. The curious thing is that there are so many books on this subject. However, there was an epoch when there were practically no books at all. So for instance, here you will see Bjorken and Rel. In the 60s, this was probably the only book that was available on field theory in the 60s. There's also another one by Bogolyubov and Chetkov, where I have a copy lying somewhere, but it's not in the office today, which is, in today's language, it's extremely old-fashioned. Then there was this book by Schweber, Relativistic Quantum Field Theory, which at the time it was written was basically only quantum electrodynamics. In the 80s, there was this encyclopedic book by Edzikson and Zubair, which is still very
Yeah,
amazing book.
that was the text that I studied from.
There you go. There you go. And in the 80s, the first book that appeared on gauge theories was this Chengen Lee, which even today happens to be a pretty good book. But somehow authors feel that no book is up to the mark. That's why every author decides to write a book. And that's the reason why there are so many. The Sredniki is a pretty good book. There's another companion to this by Schwartz, which are my copies at home, so I haven't been able to take a picture. Then there's a 3-volume series by Weinberg himself. Here's volume 3, 1 and 2. And there's a very, very nice introduction to the subject by Amitabh Lahiri and Palash Pal. So that's our Indian authors. For those of you, this is an affordable book and a good one. And these are the books which are more on the particle physics aspects. Griffiths, which I just also cited in my notes. And this book by experimentalists is also very good. It's a very nice introduction. These are very recent books by Langacker and by Burgess. These are all more difficult books, I might say. The only thing in this collection is that there's still no book that really covers the Higgs. I don't know why there is, maybe why that is so. Maybe there are other books but I'm not aware of.
That's your next job, to commission an author who's going to write a book on Higgs.
I tried to get 1 or 2 people, but I think the effort involved. I'm sure that there are some review articles and so on. I think there are 1 or 2 popular books also.
Well, maybe one of our listeners might take up the challenge.
Yes. So let me stop here and let us see what we can do and how we can take. And I take this opportunity to thank you for inviting me to give this. It took a little bit of thinking of how to put all this across, but it has been great.
Well, thank you for taking all this time. I can see the meticulous notes that you have prepared, and that which gives a hint of the time and thought that have gone into it. Unfortunately, being a a recording, we cannot say, okay, now the floor is open to questions and take questions.
Yes.
But hopefully people will follow up online, and we can continue the dialogue there. Okay.
I have sent you a copy of this picture and also these notes. So if
Yes.
somebody
Yes.
writes to you, they're welcome to to share these notes with you, and you request you to just send it to them if there is any interest.
Sure. Well, thanks you.
Thank you
Thank you
so
again.
much. Have a
And
nice
yeah,
day.
you too.
Yeah.
Bye-bye.
Bye.